Now this is another video for the lecture Intro PDE, and in this lecture we present the second part of the method of characteristic. So in this lecture we will finish section 1.5. Let us briefly recall what we have done so far. So far we have translated the first order PDE system of general form, here this one, into an ODE system, into this ODE system. And we prepared general initial value problems to initial value problems of a specific form. Namely, we now have the form that we assume that that we give the values of our solutions on a hyperplane, on a flat hyperplane H, yeah, which has the form that, yeah, here this H is a flat hyperplane. So we have here, we look for a solution and we have this flat hyperplane. And we have given our initial values, and now we want to solve the PDE. Solve the PDE on a neighborhood of some point. Okay, and this point is P0, Z0, X0 in W with two conditions. Yeah? We need two conditions. First, of course, our function. We must be in the set of solutions, and we have another condition, the coordinate which is fixed on the hyperplane. Here this is x0. Sorry, x0. This should be not 0. Yeah? These are our two conditions. Yeah, and then we know by the lemma we have the initial values. Initial values. We call them Q of y, G of y, and y. Yeah, for y in the hyperplane. Yeah, so on this hyperplane we have our initial values. Q corresponds to this. This corresponds to u, and this is the coordinate y. Okay, so what do we do? Yeah? Of course, now we use this as initial values and solve our ODE system. Yeah? Now we solve our ODE system and obtain, yeah, ODE system plus initial values gives a family of solutions. Yeah, and the family of solutions is just X. No, we want to order this in the form P. So P of S, set of s and x of s. Yeah, we want to bring this in this form. Okay. Sets should be, of course, the value of the solutions. Yeah? So in principle, we know set. Yeah? So the first thing is that we think about this map. Y s, yeah, going to x of y s. Yeah, and we calculate of this map, we calculate the derivative. Yeah, so we calculate the derivatives. Now, if we look at our ODE system here, this is given by such a derivative. So if we insert this in the Jacobian, yeah, of course, with respect to y, x is just fixed. Yeah, so the Jacobian of this matrix, of this mapping, yeah, this goes from, these are n plus 1 components to n plus 1 components. Yeah, this belongs to Rn minus 1 cross R, and x belongs to Rn. So this is really a map from Rn to Rn. And the derivative initially is by definition just this matrix. Yeah, since this components obey this equation, here this is this, and of course with respect to y, this parameterizes our family, so this doesn't depend. Only by definition we know that yeah, since these are the derivatives of this map Q. Yeah, so the initial data of the Q gives us this. So we see that we have this matrix. Okay, and now we cover again, since this expression is not zero, the determinant of this matrix is non-zero. This has full rank at s equals 0 and y equals x0. Yeah, at this pair. Yeah, so at x0 equal to x0, 0. Yeah, this has full rank. And then we know in the neighborhood, since these functions are differentiable, yeah, by the theorem on the dependence of solutions of an ODE on the initial values, we know that this whole family is differentiable, not only with s, but also with y. Yeah, there we need this theorem of ODE theory. So we know this is differentiable, this map, yeah, all partial differentials exists and are continuous, so it's differentiable. And then we can apply the inverse function theory. And by the inverse function theory, so this is locally a diffeomorphism. Yeah, by the inverse function theory. Yeah, by the inverse function theory, this is locally a diffeomorphism. Yeah, and this is now very nice, because this means we can use, yeah, this means we can use this, we can now use this map and set and define our function u. Yeah? So this means we define our function u in this way. Yeah? And so we get locally a candidate for a solution. Now it remains to show that this is really a solution. Yeah? Of course, we already know it's differentiable. Yeah? Since everything is differentiable. Yeah? This map is differentiable, set is differentiable, so it's differentiable. So we have a differentiable candidate for the solution. So we have to show now the next step is that this really solves the PDE. And this is not so easy. Yeah? We will see one step is quite easy. Yeah? And what is easy is to show that this equation is fulfilled. Yeah? We directly get this equation is fulfilled. Yeah? Because this is the equation which we used to set up the ODE system. If you remember, yeah, we used that this equation is zero. We used here for getting the ODE system in the very beginning of the last lecture. Yeah, we used this equation, and then we obtained that this is zero, the total derivative. Yeah, so, but this is the total derivative. Yeah, and since we arranged all our expressions in such a way that this equation is fulfilled, we immediately get that indeed our that we have now this equation. Yeah, so this we just get by our ODE system. Yeah, if we do here the calculations, we take the derivative as a d by ds of f of p of epsilon s, comma z of epsilon s, comma x of y of s. Yeah, this is of course df by ds. df by df by dp times p prime plus df by dz times z prime plus df by dx times z prime. I omitted here the values, yeah, and by definition of our ODE system we have chosen this free expression in such a way that this is zero. Yeah? So we know this is zero along all the integral curves, yeah, and we know f of p of y 0 initially, z of epsilon 0, x of epsilon 0. This is 0, yeah, and this together implies that f is 0 on the whole space, along the whole space. So this is already quite good. What is missing in order to obtain that this is really that our function u now solves the differential equation? Yeah, there's missing only one thing, yeah, because this is by definition u, this is by definition x, but this is not clear. Yeah, so it remains to prove that p of s is equal gradient u of x of s. This remains to prove, and this will turn out to be quite complicated. Yeah, and so this is the thing which we prove now. So we now want to show this. Yeah, if we know this, then we know that u indeed fulfills the differential, this equation. Yeah, because okay, so how we do this? Yeah. Okay, now this is the first step. We know that this is 0. Now comes the second step. In the second step, we show that we need some preparation. We need some preparation, and the preparation is that we show this equation and this equation. Yeah, And then afterwards we will see if we know these two equations, then we can conclude this. But this is now a preparation, yeah, in our second step, that we show this equation and this equation. Okay, this equation again directly follows by our definition here, yeah, because this is fixed in the ODE system and this is fixed in the ODE system, and if you insert both terms, then you see this equation is true. Yeah, let's see. Z, our ODE system, Z is the derivative of f with pj, and x is the derivative also with pi. Yeah? Also here this is this sum, and here, okay, so, and if we now do this sum, then we see immediately by definition we get the left hand side. If we do this sum, we get the same expression as the left hand side. So this is just fulfilled. Okay, and now we have to also prove this equation. Yeah? For s equals 0, yeah, for s equals 0, we know the right hand side, yeah, then is g, then we have dg by d epsilon I, this is just qi, and the right hand side, what is the right hand side? Of course, this is ji, yeah, this, at initially x is the same as y. Yeah, so this is only non-zero if j is equal to I. So we get, this is on the right hand side, we have pi, and initially these are equal. So by our initial conditions, this is true on the hyperplane. Yeah, the second equation is by definition fulfilled on the hyperplane. Okay, now we do a very nice trick. Yeah? Now we want to follow that this equation is fulfilled also along the whole trajectory. And to do this, we just calculate derivatives. Okay, as a preparation, we first do the derivative of this with respect to y. Yeah? Because this equation here is fulfilled for all y, we can take the derivatives. Yeah? And of course, taking the derivatives of y by the Leibniz rule, we have to take here the derivatives plus here the derivatives. Yeah, so we get this is just this, so we have this equation. Now we take here the derivative of this difference. We calculate the derivative of left hand side minus right hand side, yeah? And with respect to s. Of course, we want to show, finally we want to show that this is 0. Yeah? And you will see how this comes up. Okay, here we do first the calculation. Take the derivative, then we get this second derivative. And here, again, Leibniz rule. First this derivative and then this derivative. So we get this expression. Now we use that the second partial derivatives commute. So this expression here is the same as this. So we now replace this expression by this expression. So we obtain this sum. Yeah, for this we obtain this sum. And now if you look, yeah, here this expression and this expression, they also only differ by the order of the second derivative. So they are equal. This expression is equal to this expression. So if we insert in this term here, then this term will cancel with this term. Very important, yeah? For this term, we insert this term, and then this term here will cancel with this term. So only this term remains, which we have written here, minus this term. which we have written here. So it simplifies to this expression. And then now we insert. This is given by our ODE system, and this is also given by our ODE system. Now we just insert this. This is this expression. This is just the definition for the ODE system. And for this expression, this was minus of these two expressions. These two expressions. So minus gives this the sum of two. So I just inserted here of the ODE system this and this expression and get this whole expression. And now this is very nice. This is almost this expression here. Because if we calculate this expression, then we get a term where we have to differentiate with respect to p and then p with y. And this is exactly this. Differentiate with respect to p and then p with y. So if we take the derivative here, we take this term. If we take the derivative here, then we get, we almost get this term, but not completely. But if we do the calculation here, then we get this term. So then we get this term. So only the middle term here is not correct. So we get, instead of the middle term, we get this two, the difference of these two expressions. This term here is the expression which comes out in this expression here. So from this expression we have this expression, so we have to subtract it. And the other expression here, this is just this middle expression here. So we get this term. So what we have? This derivative is just this term minus this term times this term. And now this is very nice because this is exactly again this term. So we have that the derivative of this term is something plus something times this term. Now this something here, this is 0 because this is everywhere 0. This we already know. This is everywhere 0. This we have already shown. So also the derivative is 0. So this vanishes. So we end up with this differential equation. So the derivative of this expression, of the difference of the expression which we want to show is 0, or by some ODE, and some very simple linear ODE. And such a linear ODE has, of course, the solution 0. And since the initial value is 0, by uniqueness, we get that this expression has to be 0. So this is a very nice trick. We want to show that something is 0. We have defined it with some ODE system. So we just take the derivative and then we show that it itself fulfills an ODE, and then with initial value 0, and then it's 0. So we indeed showed the second claim. This now proves the second claim, that this difference is completely 0. Since this is a linear ODE, and the initial value is 0, it's 0. So we have this equality. And now it remains to calculate this. Okay. We calculate this, we define this in these new coordinates. So we use the chain rule. We use the chain rule, because we defined x as a function of y of, we have this y of s going over to x. And we already know that this is invertible. this is invertible, this map, yeah, locally. So we now first, in order to calculate this, we calculate the derivative with respect to these other variables, and then the variables with respect to xj. Yeah, okay, and then we get this. Yeah, totally by the chain rule we have to take the derivatives with all coordinates, so we get this sum here first with s, and here with the n-1 variables y1 until yn-1. Okay, now we insert this expressions, and then of course we insert this expression. Yeah, for this, yeah, we have this nice expression, so we insert this, and so we get now we just insert this, yeah, and this here we insert this, and here we insert this, and then we get this expression. And now, since we know, yeah, if we look this is of course the identity. Now here stands the derivative of this identity, yeah? And the derivative of the identity is the unique matrix. Yeah? Since we already know this is invertible, this total map is the identity, and so it has derivative 1. So the Jacobi matrix of this map here, this is of course the unit matrix. So this means it's only non-zero if k is equal to j, yeah, and then it's 1. Okay, and then we get that this is only 1 if k is j, and otherwise 0, so we get pj. And this is exactly what we wanted to show. Yeah, so this implies du is equal to p, the function du. So we have solved our PDE system. Yeah, and this now finishes the proof. Okay, now let's finally return to the examples, to the two examples we already considered before. Yeah, and the two examples which we considered before were on the one side the transport equation, and on the other side it was the scalar conservation law. So let's first do the transport equation. Yeah. So how does the transport equation look like? Now we return to the transport equation, and we want to bring it in this form. We want to understand why our solution method is exactly an application of this method of characteristics. So let us again write the transport equation. Yeah, this is the transport equation. Yeah. Here, this is the transport equation. Yeah, or maybe we do the more general. We do the inhomogeneous. Yeah, or u dot of x of t plus b times gradient u of x of t is equal to f of x of t. Yeah, okay. So this is now our transport equation which we want to solve, and we want to solve it with the help of the method of characteristic. So we have to understand how this method applies to this system. So first of all, we collect, we have t, we have an extra variable, and of course we combine this to one vector. Yeah, we combine this to one vector. So this means we have an extra, yeah, t is equal to xn plus 1. Yeah? And then this, our function, then looks like, now this function okay, for the transport equation, f looks like this. This looks like this. We subtracted the inhomogeneity, so this looks like this. And now we want to solve the corresponding ODE system. So let us look at this ODE system here. And yeah, here is the ODE system. Yeah, so the essential point is that f depends linearly on p. Yeah, also first order only. We only have first order terms. Yeah, and in this situation, the derivative doesn't depend on p. Yeah. Here, this doesn't depend on p then, and this, since it doesn't depend on set, this vanishes. Yeah? This term vanishes. Yeah, but in any case, for p dot, the differential equation is not. What we can see is these two expressions become independent. Yeah, so f is, if f depends linearly on f, this means xi prime of s does not depend on p, and set of prime of s, yeah, if we take the derivative and then multiply it by p, then we see this minus f does also not depend on p. Yeah, set prime of s minus f, evaluated of course at the corresponding point, does also not depend on p. Yeah? And since f is everywhere 0, we can set this 0. So this means we can solve the system for x of s and set of s independently of p. So we do not need p, because set describes our solution. So in this situation, when f depends linearly on p, we do not need p. So okay, let's see. In the case of now, let's do this in the case of the transport equation. Yeah, in the case of the transport equation, then we see, yeah, this plus f. Yeah, this is exactly set prime. Set prime was this linear term in the p. Yeah, and so if we add to f this term, then it's really linearly. Yeah, it's also plus constant. So it's first order. Yeah? Okay, so f in this situation, capital F minus f is plus f is really linear. So so we obtain just this equation here. Z prime is equal to f and x prime is equal to b. Yeah? And this was exactly the equation which we solved. Okay, let's understand this more general. So if depends linearly, whenever the function depends linearly, or more generally, whenever, one should write here, whenever f is a first order polynomial with respect to p, then these two expressions here, yeah, this minus this, then all first order expressions cancel. So this doesn't depend on p, and this also does not depend on p. Yeah? The same is true when f is a first order polynomial. I will change this. Yeah? When this is a first order polynomial. So then, and in this situation, we can solve the equation without solving without the p. So we can throw out the p. Yeah. So in this situation, that f is a first order polynomial with respect to p, then it's really, then we can throw out the p and it simplifies. Yeah. Now let's look at the scalar conservation law. Yeah, this was this equation. Okay, this looks like this. Again, we introduce this new coordinate, and then f has this form. And in this situation, it's really linear. It's really linear. Yeah? So scalar conservation law, f is linear. So we obtain this equation and this equation, and this were exactly the equation which solved. So we indeed see that in these situations we the method of characteristic gives back the solutions which we obtained. Okay, so let's recall what we have done today. We have finished the method of characteristic. This means we proved the following theorem. Yeah, we proved the theorem, the main theorem of this, of the method of characteristic. This is theorem 1.40. So under the assumption, yeah, we have some hyperplane, we have some point in this characteristic set, and we have this extra condition. Yeah, this is a very weak condition. This is the only extra condition which we have. And whenever this condition is fulfilled, of course for this hyperplane, yeah, if we choose another hyperplane, then this should be chosen differently. Okay, so this is these two conditions, then there exists the solutions. Yeah, and the method was very tricky. We used this ODE system, defined our candidate for the solution, and then proved that this candidate really solves the equation. And finally, we understood that the transport equation and the scalar conservation law we solved indeed exactly by this method. Thank you.